You know what's better than building a robot? Rebuilding it with a bunch of upgrades. After brutally failing on my last project, I'm back again to destroy another one. Meet my 2-year-old friend, Hola Bot. Back in the day, this little guy was my pride and joy. That for a good reason, Hola Bot was champion in the prestigious eYantra robotics competition. After waiting too long, finally I'm going to give some updates to it. But before that, let's have a closer and last look. Pretty awesome, right? If you are impressed by the design, I would love to take all the credit, but sadly I can't. This robot was actually a team effort with my few friends. We also published a research paper for the same, so if you are interested, do check it out on IEEE Explore website. I removed its uppercase if you are judging him by its current look. So what you see here is the base of the robot. This little buddy is an holonomic plotter robot and it was built to plot images and sketch the locus of the parametric equations on the ground plane. For plotting equations, it had two removable pen mechanisms, one here and another one here. And for images, a servo based pen mechanism was used. For localization or feedback, it was guided by a top view camera and then a Ruko marker placed on the top of the robot, and it did the job impressively well. That was complete story on what it was. Now the $1,000,000 question is, what is it going to be? What am I planning to update on this thing? The answer is, except the base chassis, everything. So here is the plan. I have been reading Probabilistic Robotics by Sebastian. It's a brilliant book covering important concepts of robotics like localization, mapping, planning and control, etc. But what's the point of reading a book on robotics without having a robot to test it on, right? So keeping that motivation alive, I raided my so-called inventory and found a few relevant components: a remote control for manual operation, a LiDAR sensor for mapping and localization, and a few boards to give this bot a brain upgrade. But something was still missing: the beauty from Beauty with Brains. So it was time to dust off my old circuits and give Hola Bot a fresh start. The big idea: I'm going to turn this robot into a 3-wheel holonomic indoor bot that can manually map its surrounding, then autonomously navigate from point A to point B while dodging any obstacle on its way. Yep, we are talking about SLAM, Simultaneous Localization and Mapping, with this 3 holonomic design. But the story doesn't end here. I will be building a web-based dashboard to manage it all, just like a warehouse robot. From the dashboard, we will be able to create and schedule tasks, live map of the environment with the real-time updates, with the camera feeds, and much more. It seems like a long project, but after this, I will be having an easy-to-use autonomous robot to test some robotics applications and algorithms like surveillance, pose estimation and localization using April DAX, motion control, auto docking at charging station, etc. But before directly jumping into the hardware, I decided to make it ready on the simulation first. Then we'll deploy the same thing on the hardware, then integrate the web-based dashboard for easy control, and lastly give some good looks to it. So stick around because this is about to get really interesting. Let's get started with the simulation thing first. I created a ROS2 workspace for my Hola Bot version 2. Inside that, created a package as Hola V2. Did some initial setup and it's ready for development. I have the Hola Bot base model STL files provided by eYantra. For simulation purpose I am going to use them. In order to do so, I created a URDF file which combines those STL files and defines my robot structure. Added some plugins in the URDF which were required for the Gazebo, and then prepared a launch file to launch the Gazebo simulation and spawn my robot in an empty world. Build the package and boom, I launched my robot on the Gazebo simulation. I am starting from the scratch, so here we have the base chassis only, no camera, no ladder, nothing else. Also in the model DC gear motor was used, but in the actual robot I am using a stepper motors. No worries, as far as these 3 wheels respective alignment is same with the actual robot, nothing to worry about. Now the next step, how to add manual control tool. I could have used a teleoptist keyboard package for controlling it manually from the keyboard itself, but that option wasn't seen practical to me, so I decided to add gamepad control, which gives more practical and natural feel. For capturing the joystick data, thanks to ROS I don't have to write code for it. I launched a pre-available Joy node and that was seamlessly capturing the joystick movements and publishing them on Joy topic as well. From that point I had to take over. In order to control the robot from joystick, we should be aware of the velocities associated with the robot frame. If it was a differential drive robot, due to physical constraint of the robot, we were allowed to control linear velocity in the x-axis and angular velocity in the z-axis, which results in 2 degrees of freedom. As in our case, it is an holonomic robot, so we are having the advantage of one extra controllable axis, means we can control the linear velocity in the x-axis, angular velocity in the z-axis, and not only that, we can control the linear velocity in the y-axis as well, which results in the 3 degrees of freedom. Just for explanation, if it was a drone, then we were able to control all 6 velocities, 1 linear and 1 angular for each corresponding axis, which results in 6 degrees of freedom. Now in order to give the joystick input to the robot, I added the plugin to control the robot from velocities being published on the CMD well topic. One last thing left, if you remember, our joystick data was being published on Joy topic, which was raw data, not robot velocity yet. So in the launch file I added the code to launch the teleoptist Joy node, which will publish the velocity in the CMD well topic respective to the Joy data, but before that I added the parameters which basically takes the concerned joystick input and map it to the respective velocity. After that I rebuild the package, launch the simulation, and oh, I forgot to turn on the joystick. And yes, I can manually control it from the joystick. Here you can see it is performing holonomic motion. I am giving velocities in both x and y axis while keeping its orientation constant. But one thing, you can notice some drift in the traverse path when it is going straight. So this is because I am publishing the robot frame velocities, that is Vx, Vy, Vz, not the robot wheel velocity, that is V1, V2, V3. In simple words, I am controlling robot from center, not from wheels. So while in motion, wheels are creating friction between the surface and the robot. So due to that, robot is drifting from its expected path. To solve that issue, we should transform the robot frame velocity, that is Vx, Vy, Vz, to robot wheel velocity, that is V1, V2, V3, and here inverse kinematics comes into the picture, but it's already too much for this video. In the upcoming uploads, inverse kinematics will be implemented and the LiDAR camera will be mounted on the robot, and will proceed few more steps towards the completion. So subscribe to my channel, and if you are also a robotics enthusiast, give a shot to eYantra robotics competition, and if you already did, comment down your experience. See you in the next video.